Good afternoon, we're the ECE Elbow team and we will be presenting our final presentation today. I'm Emily Scarcella, and then the teammates that are presenting is Sam Mindis and Wilfred Worland, and then our other teammates up here are Jacob Medema, Anton Inderruben, and then Josh Vernon. Help answer questions at the end. An overview of our presentation, we're going to be going over the mechanical systems, the electrical systems, and then also our testing. First, we're going to start off with our goal statement. Our goal statement was to create an ECE Elbow to assist users in two different ways. The first way was to help users that have difficulties in performing everyday tasks, such as lifting a bag full of heavy groceries, like dog food, bringing stuff in the house, stuff like that. And then the second way we were going to use it was for people who perform repetitive tasks throughout the day, such as in a factory, on an assembly line, in a warehouse, lifting heavy boxes, stuff like that. The ECE Elbow's main goal was to reduce the amount of muscle fatigue that the user feels in their muscles. I will be going over the mechanical components, so the overview of what I'll be talking about is the requirements, the device itself, which includes the actuator and the physical structure, the physical stops, the user interface, and then some future iterations. So the mechanical requirements: the device shall lift 20 to 25 pounds, it shall weigh less than 15 pounds, it also shall have physical stops to restrict the ECE Elbow's movement to a normal person's range of movement. And the user shall be able to put the ECE Elbow on and have it up and running operationally within 1 minute. To begin with, I'm going to go over the actuator. We used a motor and then a gearbox. Unfortunately, we could not use the large motor that we needed with the, we couldn't get a large gearbox with the gear ratio we needed, so we had to use a small gearbox with a large motor. So we actually had to machine out a little bit of the gearbox and then move some of the holes, but we ended up getting it to work out fine and having the gears line up fine. Some specifications from our actuator: our motor is capable of producing 3.2 foot-pounds of torque. It weighs about 0.17 pounds. It was a large chunk of our budget, $205. Fortunately, we were able to get the research grant. It has about 60 RPM for speed, and then it requires 6 to 7.4 volts. And then with the gearbox, it's a 7:1 ratio, gear ratio. We were able to get 22.3 foot-pounds of torque. It only was about half pound, and then, or 0.4 pounds, and then it cost $70. Again, our research grant covered the cost. And with the gear ratio reduction, the speed was about 8.4 RPM. So for our structure, we welded aluminum bars together. As you can see, there's blue ovals around where all the welds occurred on the lower arm segment and then the upper arm segment. And then here's our physical structure. This is an exploded CAD model view. As you can see right here, there's the spacer blocks to mount the gearbox to the upper arm segment. And then we have the drive shaft into the rotator part, and then we press fit that together. And then we had the rotator attached to the lower arm segment with cap screws, as you can see in the picture. And then for the physical structure to continue, we also used a bearing to attach the drive shaft to the gearbox and also to the upper arm segment. And there's the CAD model, and then there's our actual bearing, and then there's our gearbox. So then for the physical stops, we wanted to keep the ECE Elbow in a normal person's range of motion. So we put a physical stop to keep the flexion at 20 degrees and then an extension at 180 degrees. Here's the 20 degrees one. There's an actual picture of it up there, and then as you see, like as you are fully flexing your arm, it'll stop at 20 degrees, and then here's the next one. As you're fully extending, it'll stop at 180 degrees. The bottom rotator piece will hit that little piece of metal sticking out before it'll go past the 180 degrees, because we do not want to break anybody's arm. And then for the user interface, we used Velcro straps to attach the user's arms to the lower arm segment. And then we also, on the lower arm segment, had a piece of rubber just to make it a little bit more comfortable, because the aluminum bars were not very comfortable against your skin. And then to attach it to the upper body, we had a bar arm strap. And as you can see, right where that arrow starts, that is where we looped it through the aluminum bars to attach it to the structure, and then it just went across under your arm and then over the back, and it just Velcroed together. And then we also had the 3D printed housing to enclose all of our electronic components and our motor, as you can see right there. And then we also had a slider to completely enclose it so that nobody could mess with it. And then we also had cutouts on the side to prevent any like overheating and just letting some air in there. We had also a spot for the emergency stop button. As you can see, as it's on me, the user, it's right where I can hit it, but it's also not somewhere where I can like bump into it like on my neck or anything to like make it stop, and nobody else can like walk up to you and just hit it. Like you're not gonna bump into a wall or something and accidentally turn it off on yourself. And then also there's a picture of me wearing it just so you can see it a little bit better. So some future iterations for the physical stops. I think we would like to design the structure so that the physical stops can be placed in a more desirable position, because 20 degrees is a little bit close. It might be a little uncomfortable for the user. I mean, it'll stop the device, but it'll still be uncomfortable. And then also for the motor, we want to choose a different motor, one with a higher, like more torque, a faster motor. Also, probably not with the gears, because we unfortunately chipped a little tooth off during testing. So from the mechanical summary, what I went over our mechanical requirements. I talked about the device, the structure and the actuator, the physical stops, the user interface, and then some future iterations. So now I will hand it over to Sam to go over the electrical systems.
All right, thank you. So I'm going to do a brief overview of our electrical systems for the product that we have finished today. I'm going to go over the block diagram of our electrical systems, then go over each of the subsystems within the block diagram, then talk about future iterations, what we would change, and have a quick summary at the end. So first off, our block diagram. First thing to note is that we have power going through an emergency stop button, which will then power our Arduino and motor. This is important because we want the emergency stop to cease all power to the device when it is pressed. Other than that, we have our EMG sensors, which will read muscle activation on a user and send it as a voltage signal to our Arduino, which will then do some computations based on the signals it receives, and send some outputs to circuits that will control our motor, which will then either turn the motor on or off and control the direction of it. So moving to the power supply emergency stop button, we currently have a AC to 7.5 volt DC converter. This is just due to the fact that we could not afford a battery within our limitations of the project. So it would preferably be a battery in a future iteration. This converter also has a 3 amp limit, which is what we found that our motor is drawing at a maximum. The emergency stop button, it supplies power to the device. When the button is pressed, it will cease the voltage to the device, so it will power it off. And we found that the average time to stop the voltage going through the device is about 420 microseconds. So that's pretty low and important because we don't want the delay from pressing the button to the device ceasing to function to be very large. So going on to the EMG sensors and the Arduino. The EMG sensors, again, they'll read muscle activation on a user and then convert it to a voltage and send it to our Arduino. Our Arduino does a few different things with this input signal. First off, it does some filtering on it, so we currently have an averaging filter on it. We found that this has reduced the noise on our signals and has allowed us to have better traces. Furthermore, the Arduino will compare the bicep and triceps values to each other and also threshold values that we have set for the user. This is important because we want to be able to find whether we are going to actuate the motor in an upward or downward direction, and we don't want the two to interact with each other too much, so they don't want to go up and down at the same time. So then finally, the Arduino will output signals to the motor controller circuits that I will be going over very briefly. As you can see on the right-hand side, I have a picture of a little bit of our motor driving code, so that helps us drive the motor. So briefly, this is a very basic description of what our code is doing. It's going through setting up pins that we need to use on our Arduino. After that, it's going to read signals from the EMG sensors, and then it will, if the user is like, if the bicep is going to actuate, then if the bicep wants to, or is contracting, then the motor will actuate in the direction of upwards motion. And then if it is not, then it'll check if the tricep is activating. And then if the tricep is activating, it will actuate the motor in a downwards direction. Then if the tricep and bicep are not activating, the motor will either turn off or do nothing depending on what it was doing previously. So as you can see, this is traces that we have taken from our circuits so that we can control our motor. The bottom two are the tricep and biceps. muscle activation, the voltage that we're reading into the Arduino, and the top two traces are the direction and the motor power. So as you see, once the bicep reaches a certain activation threshold, the motor will turn on, but the direction will remain low, meaning that it's going to go in the direction of that we want it to. So moving on to triceps, it's pretty much the opposite. When the triceps reaches a threshold value in reference to the biceps value, the motor will turn on, and as you can see, the direction pin also goes high at this and will change the direction of the motor. So speaking of the circuits that we're talking about, this is our motor control circuit that turns the motor on and off. It powers the motor from our 7-volt source. That's important because we can't drive it through the Arduino. The Arduinos have 5-volt outputs and they cannot output the current that we need to drive the motor. This circuit also allows us to toggle the motor on and off with the Arduino. It also prevents current from being drawn from the Arduino, which is very important because, as I stated previously, we need about 3 amps to drive the motor, and the Arduino cannot do that. One last thing to note about the circuit is the 40 ohm resistor that we have in there needed to dissipate about 1 watt of power. To do this, we used 4 resistors in parallel to reach that value that we needed. The direction control circuit is pretty basic. We just needed to switch it on and off using the Arduino, so it's similar to the motor on and off, but just a little bit less because we're not driving it with the same voltage source as before. So it basically just switches on and off, and we'll switch the direction based on that. So moving on to future iterations of our project, couple things we'd like to change is we'd like to have a different motor. It would allow for better refinement of the code. Right now our motor and the gear ratio makes it pretty slow, so we weren't able to do too much with speed control. It's, as I said, it's slow, so the only thing we'd be able to do is make the motor go slower, and that doesn't really help out if the motor is already slow. So refining the code, we could also do better filtering of the EMGs and do more testing to see if we can get better traces and cleaner results. And we could also mess around with the threshold values for each user and then hopefully get better results from that. Another thing would be switching to a different microcontroller depending on our needs with the amount of processing we do with filtering and from our EMG signals. We might need to be more power efficient as well if we're going to switch to a battery. And then the last thing is to change EMG sensors. We chose pretty basic EMG sensors for our project based on the price. There are better ones out there that will get better traces and that would further better our results. So in summary, I talked about the block diagram of our system, and then I talked about the systems of power, emergency stop button, EMG sensors, and the Arduino, and then our motor controller circuits. And I talked about future iterations of the project. I'm going to hand it over to Will to talk about testing.
So for testing, I'm just going to go through some of the requirements that we had to test. These are the pretty major ones. We had the device weight, the lifting capacity, our continuous lifting, interpreting the EMG data, the time to operation, the physical stops, and then the electrical stop. So for the device weight, the requirement was that it has to weigh less than 15 pounds. So basically we just put it on a scale, read what it output, and found that it weighs close to about 7.5 pounds. For the lifting capacity, the user shall be able to lift 20 pounds. We decided to change it from the 20 to 25 because then we found that the motor could only maximum at stall torque lift 22 pounds. So to do this, we put a bucket at the end of the arm, and then we started at 10 pounds and put 2.5 pounds in the bucket, and then we lifted the elbow using the controller. Unfortunately, Anton had to hold the device so that way it didn't fall. But we don't want to use the EMG sensors because we wanted to have less people around the device when it was actually moving with this large amount of weight. So we lifted it to about the 90-degree position because we didn't want it to go too far. And the device failed to actually pass 15 pounds, so we unfortunately were not able to reach the weight lifting requirement. For the continuous lifting, we wanted the user to be able to lift 10 pounds 10 times continuously without resting. So to do this, we put a 10-pound dumbbell at the end of it, and basically the time is recorded for each rotation from going up and then back down, and then we sum the total time. So the results for each different rotation are posted here. And lift about 10 pounds 10 times consecutively without resting. It takes about a little less than 2 minutes, which kind of makes sense with the speed of our motor. So for interpreting the EMG data, basically, like Sam said, it has to take signals from EMG sensors and convert it into usable information for the motor. So basically, we placed EMG sensors on the biceps and triceps, and it's important to note that you have to be very careful in placing EMG sensors on the triceps because the muscle has 3 different heads. So you have to try to find the best head that's giving you the best muscle activation. And then we had to place a ground on the actual user's elbow, so that way there's just a common ground for both EMG sensors. And again, for safety reasons, we didn't want to have the device on somebody in case something did go wrong. So we collected data from the EMG sensors and some familiar graphs that Sam just talked about basically showed that the EMG sensors were and the Arduino working together to give us usable information that drove the motor, so the biceps and then the triceps. And for the timed operation, basically we just put the device on the table, oriented it in a 90-degree position, and we had Emily put it on. And after a couple tests, we found that it takes approximately 36 seconds for somebody to put the device on by themselves and have it fully operational. So the physical stops is one of the harder things that we had to do. So initially we wanted to be between 30 and 180 degrees for normal range of motion. To measure this, we basically just put the device in the utmost position to where it couldn't rotate anymore from the top to stop, and we basically just used a protractor to measure it, and we did the same for the lower arm. And then we also tested it with the motor running to make sure that these stops would actually stop it from moving when the motor was running. And as you can see here, there's the 20 degrees and the 180 degrees. Excuse me. And the reason that we couldn't get to 30 degrees was just based off of the design, so that's something that we would change in the future. The electrical stop, as Sam said, we had the electrical stop, so it needed to shut the power off within a tenth of a second. So basically, Sam graciously donated a lot of his time pressing the button about 100 times, recording all of the data. So we had the 7-volt power supply running through it, and then we used an oscilloscope to read the fall time of the power, and then just recorded all that data. And then the maximum time it took was 544 microseconds, and the minimum was 360 microseconds. These are extreme outliers, as the average time, like Sam said, was about 420 microseconds. And here's all 100 tests. So it's kind of hard to tell, but it looks like it's skewed a little right just from how frequently everything is the power shutting off at that point. So in summary, I've gone over some of the device testing, pretty much the device weight, lifting capacity, continuous lifting, interpreting EMG data, the time of operation, and both sets of stops. And as an overall summary, Emily talked to you about the mechanical system and all the components that went into that. Sam talked to you about all of our extensive electrical information, including the motor controller circuits and the Arduino. And I covered all of our testing information. So any questions?
So in the electrical system overview, there was a flowchart. Would you mind going back to the flowchart? So just a question about this. The way it looks is that if both the biceps and the triceps are on, it'll clear the biceps over the triceps. Is that how your code is currently run?
This is just I'm sorry, his question was if the biceps and triceps are both on, then it would favor the biceps over that, and if that was true, and how our code is working. So right now, this is just a very basic version of what our code is, just for the length of the flowchart that we can put on here. Right now, our code is comparing the bicep and tricep values, as well as comparing them to threshold values that we have set. And if it's above the threshold value and how many volts above the tricep value, then it will actuate in the bicep direction, and vice versa with the triceps.
Is there any way to measure if the muscle is activating other than electrical signals? Put a band around the arm, try to detect muscle flexing?
So the question was that, is there another way other than using EMG sensors? With this application, EMG sensors are the best. You could use like one of those force bands to try to, it's hard to get like you can measure how much force somebody is lifting or trying to exert, but it's hard to tell like the actual muscle activation because it's an electrical signal. So the EMG sensors are specifically designed to read that electrical signal. So getting that type of information, I don't think that there's another way other than EMG sensors.
Why could it only lift 15 pounds?
So the question was, why could it only lift 15 pounds? We were talking about that, and we're not quite sure. We think that it might be because once everything is working together, the motor might not be getting as all of the current that it's required to get to that required voltage to lift that amount of weight. And it also might be because with the 7-to-1 gear ratio, the motor is only able to lift 22 pounds at stall torque. So it might be because the motor is also getting too close to its stall torque to lift that much weight.
You had a graph or a histogram of the time until the E-stop actually shut things off. Yeah. Okay. So how did you measure you hit the button and then how did you measure the stopwatch, or how did you determine what that duration?
So the question was how we measured the time that it took for the voltage to, or I guess the time to stop the device. So what I did was when I pushed the button, I had an oscilloscope set up with voltage going into the button and then the oscilloscope on the other end of it. And then I capture the trace and then zoom in on it and see how long exactly it took.
So is that horizontal scale in seconds, or?
It's in standard deviations currently. So the max one is about 4 standard deviations from the mean, and the standard deviation of our data was about 25 microseconds. So the max, I believe, was like 530 microseconds around there. So it's still well within what we needed to do.
Okay, so what was your average was
420 microseconds.
420 micro, and then you had a standard deviation. What was your, so you had, and from that you had a standard deviation, but you're plotting how many points are outside of that?
So at the bottom, our standard deviation was 25 microseconds.
Okay.
And the
so
histogram is just showing.
You can go back, or yeah. So then the things at the end was what was concerning me. So that the 2 things that are around the 4 were actually 100 microseconds different than the 420 microsecond average.
Yeah. So our goal with the stop button was to have it cease power to the device within 1/10 of a second. So we're still quite a few orders of magnitude below that.
So you're a 20th of a second, right?
Yeah.
Okay, that's all I'm curious about. Okay.
So with 1/10 of a second stop, so I'm still not quite sure how that is useful. So I would think it'd be more useful to know from when you hit the button when the power is set off, not so much whenever basically that the switch fully disconnects. Is that what the user actually wanted?
This was a requirement that we put in for ourselves because we just wanted to have it stop within a short amount of time. As for testing when the user presses the button, it will seem like it's immediate to the user, which is basically what we were going for, but we don't have the equipment to test from when a user starts to press the button to when it actually will cease functioning the device.
Okay, so as a team required, not any testing. That makes sense.
Can you use on either or arm, or is that just for like a certain for the right arm?
So the question was, can you use it on either arm? Currently it's only designed for the right arm. Any other questions? Thank you.